next unit is our forces unit. I think you'll like it. It's one of my favorite units. And mathematically, it's pretty straightforward. What is a force? A force is a push or a pull. And Newton's first law states that an object in motion will stay in motion I'm going to add something in here. At a constant velocity. No change in speed or direction. Unless acted on by an unbalanced force. So if I went way out into space where there wasn't anything around to interact with, there's no friction, no gravity, and I threw a baseball at 10 meters per second, it would continue going at 10 meters per second forever and ever and ever without ever slowing down or changing direction. So an object with no unbalanced force is said to be in equilibrium and will move at a constant speed. We tend to think of an object with no forces on it will be at rest, but it doesn't have to be. It just has to be at some constant speed. Sometimes you'll hear Newton's first law, they'll say an object at rest will stay at rest. That's only a specific case. It's any constant speed will stay at that same constant speed unless there is an unbalanced force acting on it. So this object below has a forward force of 40 newtons and is at a constant speed. Always look for those words because you see the constant speed, you know the following has to be true. If it's constant speed, it doesn't mean that there are no forces acting on it at all. It means that the forces are going to cancel. Okay, so they are equivalent. Constant speed means their forces will cancel, means there's no acceleration. So, in this case, if it's going at constant speed, the forces all have to balance. The force of friction has to equal 40 newtons back the other way. And it doesn't mean it's going to be at rest. It just means that as long as those two forces are balanced, it's going to continue at the same constant speed, whatever speed it's at. Inertia. Inertia is a resistance to a change in speed. So going back to an object at rest will stay at rest. Let's think about that for a minute. Let's say I put a golf ball on a tee. It's at rest, wants to stay at rest. When I hit it with a golf club, I'm putting a force on it, and that's going to make it accelerate. The same thing will happen if I put a bowling ball on a tee. I hit it with a golf club, okay, and there's going to be a force on it, so maybe it'll move, but it won't move as much. The bowling ball has a much greater resistance to a change in speed than the golf ball does. It's easy to change the speed of the golf ball. It's hard to change the speed of the bowling ball. So the bowling ball has a much greater inertia. And inertia, it turns out, is just the mass of the object. Now, when we put these things together, mathematically, we end up with Newton's second law. In Newton's second law, we can write it one way, but then we're going to write it a different way. We're going to say that the acceleration that something has is going to increase with the amount of force, the bigger force it has on it. I'm going to put a net there, or unbalanced force. And it's going to decrease with the amount of mass, because the bigger the mass is, the harder it is to accelerate it. Now, the way we're usually going to see it is like this. F net equals ma. And this unit, we're going to be using this equation over and over and over again, and it's very simple and straightforward to use. So, top of the next page. All right, now applications of Newton's second law, F equals ma. Weight is defined as the force of gravity on an object. Okay, an object on the moon weighs less than an object on Earth. It has the same amount of mass, but it has less weight. Because weight isn't mass, weight is the force of gravity. Now, since F equals ma, Fg is going to be m, and we call the acceleration of gravity g, so we're going to use mg, where g is the acceleration of gravity. So here's an example. An object has a mass of 4 kilograms on the Earth. Find its weight on the Earth in part A. When it says weight, we have to know that they're looking for the force of gravity. So we can just use Fg equals mg equals 4 kilograms. I'm going to put units down here just so you see what happens. Times g, we've been using 10 meters per second squared for that. And I would get 40, and the units would be kilograms meters per second squared. Our masses in here are always going to be in kilograms. And you could write that and it would be correct, but there actually is a unit for force called a Newton. You can abbreviate it with a capital N, and a Newton is equivalent to that kilogram meters per second squared. Part B, the mass on the moon. Now, this is a trick question, okay? Let's say I threw a bowling ball at your head on Earth. That's kind of a gruesome example. It's going to be hard to stop that bowling ball, okay? And it's going to knock your head backward. The same thing is going to happen on the moon. You wouldn't want to get your head in the way of a bowling ball on the moon any more than you want to get your head in the way of a bowling ball on the Earth. It still has mass, even though it's going to have less weight. It turns out mass is always the same. So if it has a mass of 4 kilograms on the Earth, it's going to have a mass of 4 kilograms on the moon. And maybe make a note that mass stays the same. So don't get tricked when they ask you to find the mass someplace else. It's going to be the same as it is on Earth. Then the last one, the weight on the moon. So again, if we're looking for weight, we're doing force of gravity. Use this equation, Fg equals mg. But this time, the acceleration of gravity is only 1.6. So we're going to have Fg equals 4 times 1.6. And that's going to give me a force of gravity of 6.4 newtons. Okay, so its weight on the Earth was 40. Its weight on the moon is only 6.4. Next thing we need to learn about is this idea of a normal force. Normal does not mean not weird. I'll explain what it means in a second in this sense. But I have a 20 kilogram mass sitting at rest on the table. So I'm going to draw a little picture. Here's my table. Okay. And I have a 20 kilogram mass weighing on that table. Okay? Well, we know that gravity pulls down on it. So I'm going to draw the mass by itself. So we have our 20 kilogram mass. We have the force of gravity pulling down on it. The force of gravity, we can do m times g. So 20 times 10 is 200 newtons. Now, the thing is, if that was the only force acting on it, it would move down because I'd have an unbalanced force of 200 down. So there must be something else going on here. And it turns out that the table pushes up on the book. And we call that the normal force. We're going to label it Fn, but that stands for normal force. Okay? And we actually know how big it has to be. If this mass is not going to go down, it has to be the same amount up, so that is also going to be 200 newtons. We're going to find that the normal force is often the same as the force of gravity. It's not always the same. For the first few today, it will be, but don't think that it always has to be the same. The word normal, I said it doesn't mean not weird, like we say in the English language. Normal means perpendicular. And if you think of the table's surface, it's perpendicular to it. So it's always going to be perpendicular to the surface. Now, what I just did up here is something called a free body diagram. Okay, a free body diagram is a diagram showing an object and all of the forces that are acting on it. Okay, you don't draw in velocity, acceleration, you don't draw in other objects. A lot of times people are tempted to stick a velocity on there and acceleration, but it's not. It's just the forces. So our first example, where we're going to do a free body diagram, have a 30 Newton block being pulled across the table by a force of 15. There's going to be a force of friction, and then what's the acceleration going to be? So I'm going to sketch it over here. Here's my table again. Okay, and I have the block on the table, and it's being pulled forward, and there's friction on it this way. So when I do my free body diagram, I don't want to draw the table. I just want to draw the block. Okay, and I'm going to label it 30 newtons. Now, I've done something tricky here. Okay, I didn't give you the mass. I said it's a 30 Newton block. And when I do that, I'm telling you the force of gravity on it. So we have here that the force of gravity is 30 newtons. Okay. Now, it's not moving down. It's sitting on the table, so we know there has to be a normal force pointing up. And again, in this case, the normal force is going to be the same as the force of gravity because it's not moving up and it's not moving down. We have a forward force of 15 newtons pulling it forward, so I have to draw that one on there. And then I have friction. Friction always works against the motion, so we're trying to pull it to the right, so friction is going to be the left, and that's going to be 3 newtons. So there's our free body diagram, and we're going to use this to find the acceleration of the block. Now, we have one thing we need to do. We have to find the mass, and it'll turn up in a second. Now, remember, Fg equals mg. I can use this backward to find the mass. We have a force of gravity for this thing of 30 equals m times 10. So the mass of this thing is 3 kilograms. Okay. Now we have everything we need. Once we've drawn a free body diagram, we're always going to write an F-net equation. And for some reason, people forget this. Okay, they draw the free body diagram, they have everything perfect, and then they have a brain freeze and forget what to do. The next step is always going to be F-net equals ma. F-net means the unbalanced force, or what's left after everything cancels. I have 30 up and 30 down. They're going to cancel. I have 15 going forward and 3 going backward. And to get the net force, I would just do 15 minus 3. Okay, equals, we had the mass was 3 times the acceleration. This gives me 12 equals 3a. So then a is going to equal 4 meters per second squared. That's our acceleration. Okay, so if the forces are in opposite directions, to get the F-net, we are going to always subtract them. Okay, here's another example. A 10-kilogram block is pulled across a table at a constant speed of 3 by a force of 20. What is the force of friction? So again, we'll do a free body diagram. This time I gave the mass is 10 kilograms. Okay, it's being pulled across a table. It has gravity acting down on it. We're going to do m times g. You don't have to show all the detail out. It's just going to be 10 times 10 for g is 100 newtons. Okay. What other force has to act on it? Well, it's not going down through the table, so there has to be a normal force upward, so Fn, and that's also going to be 100 newtons. Okay. There is a forward force of 20, and then there's a backward force of friction. We're trying to find out how big that is. Now, there's a couple ways to do this. I'm going to do the detail out. We're going to do F-net equals ma. Our forward force is 20 minus Ff. The 200s are going to cancel, so we don't have to worry about those. Equals, the mass of this thing was 10, and acceleration. Now, it says it's being pulled forward at a constant speed of 3 meters per second. Don't stick that in for the acceleration. The trick with this one is it says a constant speed. Constant speed means our speed isn't changing, we have no acceleration, so a is 0. So 0. So 20 minus Ff equals 0, FF equals 20 newtons. Now, we wouldn't have had to do all that in detail. Okay, I wanted to show you how it works out. But if you see the words constant speed, remember that that means that the forces cancel. So I could have skipped this whole step just by realizing if the forward force is 20 and I'm going constant speed, the backward force has to be 20. Now, the next one. We have a whole system of objects, and we're going to find its acceleration. Okay, so you draw a free body diagram for each object. So we have this 4 kilogram mass. Okay, we're assuming, I think, that the table is frictionless, so we're not going to have friction on this. I know I have gravity down. That's going to be m times g, so 4 times 10 is 40 newtons. I have a normal force up. That's also going to be 40 newtons. And I have this string pulling it forward. I don't know how big that force is. For strings, we label them T for the tension in the string. Okay, so that's that block. Now, again, I said the step that people forget is once they've drawn the free body diagram and all the forces on it, then they have to do an F-net equation. There's no backward force in this case. So we've drawn all the forces. We're going to do F-net equals MA. The 40s are going to be canceling. And what's left to be the net force is T. You can think of T minus 0, but it's just T equals 4A. Now, I'm going to put a box around that guy because I'm really happy that I have an equation of motion. Okay, and I want the grader to see that because I want to get credit for it. Because a lot of the problem is just getting these equations right. The second block, the 2 kilogram guy. Okay, well, we know gravity's working on it. We're always going to have gravity. Fg equals m times g. 2 times 10 is 20 newtons. Okay, now you might be tempted to put a normal force on it because we've had normal forces opposing gravity every time, but the normal force is between two surfaces, like the table and the block. This isn't sitting on a surface, so there's no normal force. But there is something pulling up on it. It's this string. And it's all one string, so it's going to have the same tension as the other string. What's my next step? Once I've drawn the diagram, I always do F-net equals MA. Now, the 20 and the T are in opposite directions, so I'm going to subtract them. But do I do 20 minus T or T minus 20? And this question comes up a lot. The way I think of it is, which one's going to win? I know that this block is going to move downward. Okay, there's no friction holding the 4 back, so the 4 is going to be pulled to the right, and the 2 is going to go down. So in that case, the 20 is going to win, so I do 20 minus T. So you look at which direction it's going to go, and you make that direction positive and the opposite direction negative. So 20 minus T equals 2A. There's another equation of motion. I'm going to put a box around that because I'm happy that I got that. Now I have to solve this. There's a couple different ways to do it. It's simultaneous equations. What I like to do, actually, is just add the two equations together. So I take this equation, T, and I add the right side of it to the right, I'm sorry, the left side of that equation to the left side of the other equation. So T plus 20 minus T equals, then I add the right sides, 4A plus 2A. If you've done everything right, the T's will cancel. So that's kind of a hint that you're on the right track. If they don't cancel, you know you made a mistake somewhere along the line. This simplifies to 20 equals 6A. And then solving for A, I get A is 20 divided by 6, which is 3.3 repeating meters per second squared. So there's my answer for that one. Okay, this has been kind of a long one, but we have one more example. Okay, the acceleration of the system below, it says here, assume that M2 is bigger than M1. And don't be afraid that we don't have any numbers on here. Okay, so looking at this thing, we're going to draw a free body diagram. So here's M1. What forces are acting on it? Well, I have gravity pulling it down. I do M times G. And in this case, it's going to be M1G. I don't even want to put numbers. I don't want to put 10 in here. I want to use G because this is just a generic problem without any numbers in it. The other force, it's not on a surface, so there's no normal force. There's just a tension pulling up on it. So that's the free body diagram for that one. What do we do once we finish the free body diagram? We write an F-net equation. So F-net equals MA. Okay. Now they're in opposite directions, so I'm going to do M1G minus T or T minus M1G. We have to know which way it's moving, so that's why we had to say this here. Assume that M2 is greater than M1. So this block here, M2, is the heavier of the two. So if that one's heavier, I know that one's going to move down, this one's going to move up. Notice I don't put those arrows showing directions on the free body diagram itself because they're not part of a free body diagram. You only put forces on a free body diagram. But I draw these to remind myself which way they're going to be going. So since this one's going up, the tension's going to win, and I'm going to get T minus M1G equals M1A. Okay, MA, but this mass is M1, so I have to put M1 in there. There's my equation of motion. Put a box around. Now, for my second one, I have M2. So I have the force of gravity downward, which is going to be equal to M2 times G. And this also has a string pulling up on it, so it has a tension up. Once I've drawn my free body diagram, I do my F-net equation. Okay. This one is going to move down, so M2G is going to win, so I do M2G minus T equals M2A. I'll put a box around that guy too. All right, now, my next step, what I've been saying is I add the two equations together. So I take the left side of this first equation, T minus M1G, and I add it to the other equation. So plus M2G minus T equals, line here so I can keep them separate, M1A plus M2A. I know I probably am on the right track because the T's cancel. And I'm going to rearrange this just because I don't think it looks very pretty. I like having the positive one first. So M2G minus M1G equals, and I can factor an A out of this side, and you'll see why I want to do that in just a moment. M1 plus M2 times A. Since I'm trying to solve for A, I have to get the A by itself, so that's why I factor the A out. Now, in order to get the A by itself, I have to divide by this M1 plus M2, because that's what it's being multiplied by. So my final answer is going to be M2G minus M1G over M1 plus M2 equals A. So we're going to be practicing this a lot, drawing a lot of free body diagrams and solving for acceleration. And I think you're going to find that you like it, it's not too terribly difficult, and you're going to be pretty good at it.